Okay, at the end of the last video, we left with this exercise where we wanted to find the series expansion for ln of 1 plus x. So first off, let's just recall that 1 plus x we derived and saw that it was negative 1 to the n, x to the n, where the absolute value of x had to be less than 1. So now what we do is we integrate both sides with an indefinite integral, and we can insert, this starts at 0. We can insert the integral into the infinite sum, giving us the following equation. And so on the left-hand side, we get ln of 1 plus x is equal to a constant plus n equals 0 to infinity, negative 1 to the n, and here we get x to the n plus 1 over n plus 1. So, overall, what we want to do now, all we want to do is figure out this constant. And right now we know that this will converge for x less than 1, but now the endpoints may change. So recall that when you integrate, the radius may change, but the interval of convergence, the radius is the same, but the interval of convergence may same. So r still equals 1. But before we get to the actual, that part, let's just solve for c. So let's plug in x equals 0. Again, notice that's the center of the series. So we get ln of 1 is equal to c plus, and then all these terms are 0. So we get 0. So c is ln of 1. Well, ln of 1 is 0, so c itself is 0. Hence, we have ln of 1 plus x is equal to the summation negative 1 to the n, x to the n plus 1 over n plus 1, where n starts from 0 to infinity. Okay, so now the question is, what is the interval of convergence? So we know that this already converges for x less than 1 in absolute value. So the endpoints, so we have to check endpoints. So we plug in x equals 1, and what do we get? We get negative 1 to the n, 1 to the n plus 1 over n plus 1, which is the series just negative 1 to the n over n plus 1. And if you look at this, I'll leave you to check that this converges by the alternating series test. We've done a few of these, so converges by the alternating series test because it's an alternating series. The terms outside of the negative 1 to the n, the 1 over n plus 1 is positive. It's decreasing, it goes to 0. So that converges. However, if we plug in x equals negative 1, then we get the following. N equals 0 to infinity, and then we have a negative 1 to the n, and a negative 1 to the n plus 1 over n plus 1. That's going to give us negative 1 to the 2n plus 1. Over n plus 1. Let me just put a little dividing marker here. Now negative 1, 2n plus 1 is always odd. So this is always just negative 1. Which is the negative of 1 over n plus 1. And this, even though it's negated, overall this series, you can think of just this series in parentheses. The series in parentheses here, it's almost exactly, well, actually, this is exactly the harmonic series, and this diverges. This is a p-series, essentially a p-series, okay? So it doesn't, so our overall interval of convergence, so what we have, let me summarize, what we have is that the ln of the absolute value of 1 plus x is equal to -1 to the n, x to the n plus 1 over n plus 1. And this is true for, well, it's not true at -1, but it is true at 1. So our interval here, our interval of convergence is open at -1 and closed at 1. Okay, so that was the exercise from the last time. And all that's left is we're just going to do one example of using differentiation. So we're going to use differentiation to find a power series expansion for the function f of x is x over 1 plus x quantity squared. Okay. So what we're going to note is, so note, because we want to always, I mean, most of these are, we're always going to relate it to somehow 1 over 1 minus x or 1 over 1 plus x or something like that. So we note that, well, this is equal to x times 1 over 1 plus x squared, which is x times the negative of the derivative of 1 over 1 plus x. Because the derivative of 1 over 1 plus x is -1 over quantity 1 plus x squared. We can write 1 plus x as 1 plus x to the minus 1th power. Take the derivative, you'll get -1, 1 plus x to the minus 2, which is exactly what we have here. So essentially, this is equal to minus x times the derivative of 1 over 1 plus x. And that's the way we're going to think about it to write it, because this now is, we know the series expansion for this, the 1 over 1 plus x, and we can take the derivative of that. Okay, so this is the idea of the problem. Let's now do it. So we know that 1 over 1 plus x is -1 to the n, x to the n, for x less than 1 in absolute value. And if we differentiate term by term, so d by dx of 1 over 1 plus x, on the one hand, well, this is equal to, let's write it on the other side here. We have -1 to the n, x to the n, whoops. This is equal to d by dx of all this, which is equal to d by dx. And let me write it term by term so we see it exactly. We have 1, when n equals 0, we have 1, and then minus x plus x squared minus x cubed, and so on. So what do we get? We get -1 plus 2x minus 3x squared plus so on and so forth. And that is equal to -1 over 1 plus x quantity squared. Well, I guess we can multiply both sides by -1, now that I'm thinking about it. 1 over 1 plus x quantity squared is equal to 1 minus 2x plus 3x squared minus da-da-da-da-da. So 1 over 1 plus x quantity squared, if we want to write it as this in a single summation notation, we can write it as -1 to the n, and then we'll need n times x to the let's see, so for this one we're going to need to start at n equals 1, so we'll have n minus 1 here, and this I guess should be n minus 1 as well. Okay, so let's just check this out. So when n equals 1, we get -1 to the 0th power, which is 1 times x to the 0, which is 1, so we get 1. The next term, we plug in 2, we get -1, and then 2 and a single power of x. So this is going to correspond correctly. And this is for, well, this is for sure when x is less than 1. Again, it may change, so we'll see that, and we'll check the endpoints in just a moment. But what we know right now is that 1 over 1 plus x quantity squared is equal to, let's rewrite this, -1 to the n minus 1 and x to the n minus 1, and equals 1 to infinity. So hence, if we wanted, our original function that we wanted was x times this. So we wanted, so x over 1 plus x quantity squared is just multiply everything by x. So we -1 to the n minus 1 and x to the n, because I multiply both sides by x. And now what we have to do is we have to check the endpoints here. So let's check the endpoints. I guess this is easy enough for these endpoints to just do it right here. So if x is equal to 1, what do we get? We get 1 to the n here is always 1, so it's just -1 to the n times n. Okay. And this clearly diverges by the divergence test. Right? As n goes to infinity, these individual terms, these go to plus or minus infinity. It kind of alternates, right? As n grows, it grows to positive infinity, but it's alternating, so it's kind of going larger on the positive side and then larger on the negative side and swinging back and forth. So this, in particular, an doesn't go to 0. So in particular, these individual sequence terms don't go to 0, hence the series diverges by the divergence test. And it's a similar deal for -1. For -1, we get -1 to the n minus 1 times n times -1 to the n. And so overall, we have a series -1 to the 2n minus 1 times n, which is actually just a series -1 times n, because that's always an odd number. And again, this diverges by the divergence test. By divergence test. So we actually get exactly the same interval as the original. So this is true for x less than 1, because both of the endpoints fail to converge at the endpoints. Okay, so that's it for that problem, and that's actually the end of. So this is the end of 11.9.